In this video, we're going to do section 2.1, which is about sets and Venn diagrams. So let's start with sets. Sets, let me define that. A set, it's actually kind of an easy definition, is a collection of objects. And that's the definition. um, so when you say something is a collection of objects, that means you should kind of know what the objects are. All right. And that's what we need to understand for a set. Now we have seen some sets already, actually. We saw the natural numbers. The natural numbers are a set. Those were the set that went 1, 2, 3, 4, dot, 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 right? On forever, starting with 1, also known as the counting numbers. We saw the whole numbers, just like the counting numbers, but they include 0, dot, dot, dot. And then we have the integers. Oops, integers. Those included positive and negative whole numbers. So I have dot, dot, dot in both directions, one going to negative infinity and one going to positive infinity. And there we go. So these three are all sets. Now, they all happen to be infinite sets. They go on forever. They don't end. And this notation that I have been writing with them, where I include this kind of squiggly bracket, I'm sure it has a formal name. I don't know what it's called. I call it squiggly bracket. This notation is actually a set notation. When you see it, they are referring to a set. In fact, when you're listing out the set like I just did, they call that roster notation. Almost like you're listing a roster of what's in the set. Okay. But there are other examples of sets, like, for example, all students enrolled in math 211 at OCCC. So that would be an example of a finite set. Since we're talking about a set number of students, a small number of students, and it doesn't go on forever, I could list everyone in the class, but I'm not going to do that. But as I'm showing you, sets don't have to be numbers. In this case, this set would be names. We'd be talking about people. So it is possible to have a set not be numbers in actual objects. Okay, that's why it's such a vague definition. Okay, let's go ahead and do another definition here. So I'm going to have quite a few definitions here. Any member of a set is called an element. So what we're going to do is kind of formalize some of the words, and we're going to also start looking at notation used to talk about sets. Okay. An example here. Let's say I'm going to label this set. The set O is all cities in Oregon. Right? Portland, Eugene, Newport, Yachts, I don't know, right? Name cities, they're in Oregon. Cities in Oregon. Again, another example of a finite set. Okay. So an example here of an element. So Newport would be an element. Of the set O. Okay. And there's like a special notation we use to represent element. So I could say Newport, and then this notation It's actually the Greek letter epsilon. Okay. So if I say Newport epsilon O, in math, this epsilon here, that represents element. So I read that Newport is an element of the set O, and O is defined to be all cities in Oregon. So we're going to be really exploring notation and getting some definitions in this section. Okay. Speaking of that, there is a special set I want to mention, the empty set. As it implies, it is a set that has no elements in it. They also call that, some books might refer to it as a null set. That's another phrase they use. Null is like, I think, a British version or a European version to imply empty. The notation we use to represent the empty set is a circle with a diagonal line through it. That represents the empty set. Or you could use the squiggly bracket and just don't put anything inside, like squiggly bracket with nothing inside. That also represents the empty set. So you could use either of those to say that we're talking about the empty set. They have no elements in them. And we'll see some examples that will be the empty set. Okay. So speaking of examples, and I'm going to kind of, the way I've decided to set this up is we're going to kind of use this example I'm about to introduce as I'm also introducing definitions. So we're going to keep coming back to this example. All right. So I want to consider the set of whole numbers up to 10. Okay. So since we're talking about whole numbers, that means we're going to include 0 in it. I'm going to list them out. And it's going to basically be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And since it says up to 10, I'm going to include 10 in the set. All right. I'm going to give this set a label. I'm going to call it U. And I did that on purpose. U often represents what we call the universal set. And it's implying that this is the universe we're working in for this example. So the big set, quote unquote, the end all and be all of this example is this set here, the 0 through 10. And I'm going to be referring to other sets, but this is the universal set. And all of those other sets are going to kind of exist within this set. Okay, so here we go. Part A. I'm going to create the set A, which is all even numbers. Oops. Have to put the N, all even numbers. So since we're living right now in this universe, A is going to be all the even numbers that happen to be in the universal set U. So I'm going to list out all the even numbers in my roster notation here. And I think most of us are familiar. 2, 4, 6, 8, 10 would all qualify. But noticing the pattern, the fact that, oops, sorry, wow. Gotta let that disappear. Noticing the pattern 2, 4, 6, 8, 10. 0 would qualify in that pattern, right? Where it's kind of skipping every other one. So I will go ahead and include 0 as one of the even numbers for this particular example, just because it follows the pattern. So A is 0, 2, 4, 6, 8, 10. Cool. Okay, let's look at another set. Again, living in this universe. So let's create the set B. This time, B is numbers less than 4. Less than 4. Okay, so from the universe, all the numbers that are less than 4, well, let's see, that would qualify as 0, 1, 2, 3. And that would be it. It won't include 4 since it's strictly using that phrase less than 4. Okay, and in math, that means 4 would not qualify. Okay, cool. All right, so let me go ahead and introduce a definition here. And we'll come back to the example. So I'm going to kind of take a break from the example and I'll come back to it. So definition, the intersection of two sets, which I'll go ahead and call capital X and capital Y. So of two sets, X and Y, are elements they have in common, the two sets have in common. So the intersection of two sets, X and Y, are elements they have in common. We do have a notation for that. X upside down U, Y. That means the intersection of X and Y. That's how we read that notation. So let's apply that to the example we just have above. I'm going to kind of zoom out a little just so I kind of try to keep it all on the screen here. So I took a break here. I'm coming back to my example. This will be part C. What is A intersect B? For the A and B, I have above. I did a squiggly bracket instead of question mark. That's funny. Okay, so I want to figure out what A intersect B is for this A and B above here in red. So I'm going to kind of give myself a little space here. So I'm looking for the elements the two sets have in common. I want to know what they both share in common. So they both have 0. They both have 2, and that's it. So coming down here, I'll put 0, 2, and there it is. Those are the elements those two sets have in common. All right. Another break from the example to give another definition. A Venn diagram is, I don't know why I capitalized the D. V needs to be capitalized because it's based on a mathematician, but D did not, sorry. A Venn diagram is a visual way to display sets. So it's a way for us to kind of visualize what the sets look like. So I'm going to return to my example. This will be part D. I want to draw a Venn diagram of A and B. Wow, that is not how I spelled diagram. Oh, yeah, no, it is. Just kidding. Wow, sorry. It's the capital. It threw me off again. A Venn diagram of the sets A and B. Okay, so here's how we're going to do that. To do this visualization, I need to include the fact that I have a universe. Here, actually, let me use a different color than blue. Let me switch to black. And the way I draw or depict the universe is I use like a big box. So this is the universe. Within the universe, we have two sets. We have the set A and the set B. Now notice I specifically drew it so that A and B have like an overlap. I probably should have maybe done it a little bit bigger even. In fact, here, I'm going to take a second and do it. Fix the second circle so it's just a little bit bigger. Yeah, a little bit bigger overlap is what I was trying to go for. Here's A and here's B. And then here's the universe U. Okay. So A and B happen to be part of this universe. A is all of the even numbers. B was all the numbers less than 4. And A and B had 2 elements in common. It had the elements 0 and 2. So I'm going to put 0 and 2 here in the overlap of A and B. Those are those 2 elements that they have in common. A also had 4, 6, 8, and 10, which I'll go ahead and put over here in A. I'm using commas just to kind of distinguish between them, but I mean, you could just kind of float the numbers in there if you wanted. B had the numbers 1 and 3 also in it. See, I floated them in the space. It doesn't have to be in order. Okay. But there are also some numbers not accounted for at all in A and B. Okay, but they're in the universe. In particular, 5, 7, and 9, right? Because 5 is not accounted for, or 7 or 9 in the even numbers for A, and B happened to stop at 3. All right, that was its largest number. And there you go. This is a Venn diagram displaying the sets A and B that we created within the universe. All right. So this type of graph, what's kind of cool about it is it's, like I said, it's depicting when two sets have in common. The graph or the diagram is depicting overlapping sets. They have something in common. Okay, that's supposed to be an O. Looked kind of sad. Let me fix it. There we go. They have something in common. Great. Okay, now, surprisingly, I'm not going to give you another definition. We're going to actually continue with our example here. Oops. Part E. Let's create a new set, and that's the set of odd numbers. Okay, so within our universe, the odd numbers would be 1, 3, 5, 7, and 9. So that's what's contained in the universe that we defined earlier. All right. Now, let's find, or let's say, what is A intersect C? So remember, A is the even numbers and C is the odd numbers. And the intersection is what they have in common. Well, they don't have anything in common. So A intersects C is the empty set. And that's how we could write it. Or you could write it the open brackets with nothing inside. Okay. Now, what would that look like as a Venn diagram? So here, let's create a part G. Draw a Venn diagram of A and C. It's a weird looking M. Let me fix it. There we go. Okay, so I'm going to draw a diagram. Now this time, though, I'm not wanting to draw the sets overlapping because they don't have anything in common. They still live in my universe U. So I'll still draw the universe U. And here's the set A. But because they don't have anything in common, I'm going to separate the two sets. So here's the set C. In A, we have 0, 2, 4, 6, 8, and 10. And in C, we have 1, 3, 5, 7, and 9. And then actually, there's nothing outside, nothing that has not been accounted for in U. So everything that's in A and C is what's in U. All right. And there we go. That would be the Venn diagram. So these sets, when they're separated like that, are called disjoint sets. And they have nothing in common. In common. So we have overlapping sets, and then we have what we call disjoint sets. All right. Let's take a moment again, and we're going to go ahead and do another definition. So I'm going to take a break from my example to give another definition. The union between two sets, X and Y, so I'll just keep referring to those. I'm sorry, I'm going to say X or Y. I'm actually going to make a distinguishing of the language there. X or Y is the set of elements that are in X or in Y or in both. What's nice is the definition kind of implies an American expression of union, meaning it's almost like we're uniting the two sets together. That's what the union is doing. So a union between the sets takes the elements in each set and puts them together. The notation for union is also really nice. It kind of plays on the notation we saw for intersection, except it's the right side up U. Sorry, kind of sloppy. So I don't put a tail on it just because I'm trying to distinguish it between union and when I'm drawing the letter U for universal set. So I kind of try to do it like that. Wonderful. All right. So now that we kind of have an idea of this definition, let's try to apply it into our example. So back to our example. We are now on part H. We're going to find A union B. Sorry, my thing was going slow there. Sorry, find A union B. There we go. Okay. So real quick, I'll just rewrite A and B just so we remember. So A was the evens, B was less than 4. All right. Okay, so A union B. So we're going to take the evens and combine them with the numbers that are less than 4. And we don't have to repeat any elements. So if A and B have something in common, we don't have to list it twice. Okay, so A starts with 0, but we'll also include 1 because that's in B, 2, 3, 4. But now I'm only going to include what's left in A. So all of these elements right here, these first 4 elements represent what's in B. Okay. And here, let me go back. And then these elements here represent what is in A. Oops, sorry. It got mad because I clicked off of it. Sorry about that. There we go. So these are the elements that were in A. And I didn't have to repeat 0 and 2, even though they were in both of the sets. Okay. And it doesn't include everything, oops, that was found in U. It just includes what was found in A and B. All right, and there you go. That's the union. Okay, I'm going to go ahead to kind of up our example a bit here. I'm going to create a new set. We'll call it D. D are multiples of 3. So I'm using a math word that might have been a while since you've seen multiples of 3. So multiples of a number mean you take 3 times a number and get that. So 3 times 1, 3 times 9. So 3 times 1 is 3. 3 times 9 is 27. Those are all multiples of 3. Okay. Any number that we can get from multiplying 3 by something is a multiple of 3. Or another way of saying it is any number divisible by 3 is a multiple of 3. Okay, so in our universe, multiples of 3 would include 0 because 3 times 0 is 0, 3 because 3 times 1 is 3, 6 because 3 times 2 is 6, and 9 because 3 times 3 is 9. And that's it. Those would be the numbers that are multiples of 3 in our universe. All right. So now that I've created this extra set, I did that for a very specific reason. I now want to draw a Venn diagram of 3 sets. So we're going to draw a Venn diagram of A, B, and D. All right. So let me go ahead and shift this up a little bit. So A was the evens, B was the numbers less than 4, and D are multiples of 3. I don't need the box that wide. Okay. So, all three sets do have things in common. There is overlap. So I'm going to draw the sets so that they all overlap each other. So here's A, here's B. Oops, let me go ahead and make that look like a better B. And here is D. I'll draw that below and have it overlapping both of those. Okay, cool. Now, what is in common in all three sets is 0. All three sets have 0 in common. And here, let me just write A really quick off to the side and B and D. So A is 0, 2, 4, 6, 8, 10. B is 0, 1, 2, 3. And then D, I have above, is 0, 3, 6, 9. Okay, so referring to that now. So all of them have 0 in common, and that's it. Okay, so A and D, what do they have in common? All right, they both have 6 in common, and that's it, other than 0, which I've already accounted for. I put that in the very center of all three overlaps. Okay, now B and D, let's see, what do they have in common? It looks like they have 3 in common and 0, but we already accounted for that, so 3. All right, and now let's see, A and B have in common 0 and 2. So we'll put the 2 right there. Okay, now what's left is I'm going to put in each set what's in only their set, not in any of the overlaps. Okay, so for A, 4 and 8 are still unaccounted for. Oops. For B, 1 is unaccounted for. And for D, 9 is unaccounted for. All right. And is there any numbers in the universe still that we haven't included? So let me go ahead and put my universe out here. And the answer is yes. 5 and 7 are unaccounted for. Oh, and I just remembered A also has a 10. Sorry about that. Here, I'll throw a 10 in there. So 4, 8, and 10. And 6 is already accounted for, so it's 2, so 0. All right, and there we go. So 5 and 7, that's sad looking 7. 5 and 7 are sitting out here in the universe in none of those sets. And that would be how the Venn diagram looks for 3 sets. Okay, I want to do one more special example for Venn diagrams here that I think will be useful to you. And that will be, I need to create another set. So, okay. Part K, let's create the set E, which will be multiples. Sorry, I don't need the squiggly. Multiples of 4. Okay, so to actually find multiples of 4, I will use my squiggly in the universe. Okay, so like multiples of 3, I'm looking for numbers that when you do 4 times that number, it, that's how that number comes about. So 4 times 0 is 0. 4 times 1 is 4. 4 times 2 is 8. And that would be it, because 4 times 3 is 12, and that goes outside of my universe. There we go. Finally wrote the magic number there. Okay, so there we go. That's E. And part L here, I'm going to draw a Venn diagram. For A and E. Depicting sets A and set E. So set A is the evens, and then set E is multiples of 4. Okay, so here, getting my universe going. Okay, so here we go. To draw this, I'm going to draw A, and then I have to kind of decide how I'm going to draw E. So A is, just writing it again since I don't have it on my screen, 0, 2, 4, 6, 8, 10. Okay. And what I notice is that everything that's in E, every element in E, 0, 4, and 8, also happen to be elements in A. Okay, that's a special relationship. And I'm going to say what that relationship is, and then I'll define it in a second. So E is what we call a subset of A because all of its elements are found within A. And to depict that as a Venn diagram, I'm going to draw E inside of A, indicating that all the elements of E are also all inside of A. So E is 0, 4, and 8. And then the elements in A that aren't accounted for are 2, 6, and 10. Sorry, that's kind of like a sad looking 8. I'm going to try to fix it. All right. And then everything else in the universe, basically all the odd numbers, 1, 3, 5, 7, 9, they'll all sit out there in the universe. And there we go. That would be a Venn diagram depicting this relationship. So here, let's take a moment and define what I just said, the subset. So definition. X is a subset of Y if all elements in X are also in Y. All right. Give myself a little space here. So that's a subset. And there is a notation we use for subset to indicate that one set is a subset of another. It's almost like the less than or equal to bars, except we use like a U. So X is a subset of Y. That's what that notation indicates to us. Technically, you could do it without the little bar saying that it's strictly smaller than what Y is, but having the little bar underneath implies that X could possibly be exactly the same as Y. All right. I'm going to go ahead and put in one more definition right now since I've taken a break from the example, and then we'll come back to the example, and it'll probably be the last one I do after this. The complement of a set X is every element in U, referring to the universal set, that is not in X. So the complement of X means it's all the things that are in that aren't in X but are in the universe. So basically every time I've been putting things out in the universe that weren't in the sets, those are complements. The notation we use for complement of a set is this like little, like they call that prime notation. Okay. X prime, that's kind of the math word we use. It's like a little slash, almost like a quote, almost like a 1, but it isn't. It's kind of supposed to be like a slash, almost like a slant. So X prime. All right. So I want to return to the example above. Part M, I want to find A prime. So back to our original set A that we've been working with, the complement of A. So everything that isn't in A. So A was the evens, therefore A complement is the odd numbers. So 1, 3, 5, 7, 9. That would be A complement, which we also happen to call another set, but that doesn't matter at the moment. That's the complement. And there you go. There's set definitions and notation. And then I'm going to do a follow-up video where I do kind of a complicated example talking and discussing the notations.